Today I am going to deal with some important facts about physics. As the weightage this time, the weightage is given to your in electric charges, electric potential, electric field, electric current, so and moving charges. So this time uh, we the weightage is given to first to say charge, then second is your electric field, and then third is your potential, and fourth, that is electric current, and fifth is your moving charge. So here I want to start here that this time the weightage is given to charge, electric field, potential, electric current, moving charges. So I am going to deal with some of the important facts about this. Some of the important facts about it. That is, the main fact is that how the book is designed. There is a charge. So when there is a charge, so there is a field. So when there is a charge, there is a field. And when there is a field, then there is a potential energy. When there is a field, then there is a potential energy. And when there is a potential energy, we have work done. And when there is work done, we have potential. And when this is about the electrostatics, but when this is about electrostatics, but when a charge moves, then it becomes electric current. So you see that all these are interlinked, and so this time the weightage is given to all this. More weightage is given to all these sub chapters. So I am going to discuss only the important point where it will help you to solve the problem, and some of the problems which students face. To clarify that, I am going to discuss about it. So here you will see that one thing you will see here, that as I have told you, when there is a charge, that means there is an electric field. So when there is an electric field, that means there is an electric potential, that means a potential energy. That means potential energy is nothing but it is work done. And when there is work done, we come to potential, and from that, if the charge is moving, then it becomes electric current. And in electric current, the charge are moving with a velocity that is the drift velocity. So here charge, then we comes to the Coulomb's law. So here in the Coulomb's law, this is the basic law, which is here F is equal to K Q1 into Q2 by modulus by R square. So here you see that this is the magnitude. Here you see that magnitude of Q1 and Q2 is taken. So here the important point here while calculating that the sign is not concerned. The sign is not concerned because we are taking the magnitude. So I want to tell you that while calculating the force in Coulomb's law, the magnitude of the sign of the charge is not at all concerned. If it is minus q, a electron or a proton, the minus is not concerned. We take only the magnitude. This is the first point. And similarly, here you see that where the most important, the point which I have told you, that while calculating the Coulomb's law, your charge, the sign of the charge is not concerned, because F is equal to K, that is modulus Q1 into Q2 by R square. Your charge is not at all concerned. Now, when there is a charge, that means there is an electric field. You see, when there is a charge, there is an electric field. So electric field, the formula of electric field is that it is a vector quantity, and so it is say Q by 4 pi epsilon naught R square, and it is a function of position vector, so R cap. So here you see this is the magnitude and this is the direction. What I want to tell you, the most important point while calculating electric field, your Q will be always will be positive. Your Q will be always will be positive. Your Q will be positive. The electric field, the direction of the electric field is controlled by this. Whether it is negative or positive, it is decided by this. The direction of the electric field is decided by this. But the Q charge, the always you have to take positive in case of electric field. This is the important point which I want to tell you. The Q here will be positive. On the electric field is the direction of the electric field will be controlled by this, because this is a vector. So how this happens? So you see, you have found that in case of a dipole, say this is Q and this is minus Q, and the distance is 2a. If your electric field is in the direction of this is the electric field for this Q. So if your electric field is in the direction of the dipole moment, that is from minus to plus. The direction of the dipole is from minus to plus. That means if your electric field is in the direction of because of this Q, the electric field at some point here P, it is in this direction, and if your electric field is in the direction of the dipole moment, that is from minus Q to plus Q, then your electric field will be positive. Electric field will be positive. That means it will be Q by 4 pi epsilon naught R square dot R cap. But if for minus Q your field direction is inward, that is E minus Q, your field direction is inward. So since your field is in the direction opposite to that of the dipole moment, opposite to the direction of the dipole moment, so your electric field will be, because of minus Q, it will be negative. Because of minus Q, it will be negative. So what I want to tell you, these are the important facts. You must remember that most of the students finds difficult by finding electric field if it is a minus Q charge, whether here the sign will be minus or plus, but there is no, the Q will be always positive. Only the direction is controlled by this R cap. So what I want to tell you that if EQ is in the direction here, if electric field at this point, because of this charge Q, it is outward, it is in the direction of the dipole moment, so your EQ, electric field at this point P, will be positive. And because of this negative charge, it is inward, here it is inward, so the direction of the electric field is opposite to the direction of the dipole moment, so it is taken as negative. So this is the important fact. So while calculation, your Q will be positive, only the electric field will be determined whether it is in the direction of the dipole moment or it is in the direction opposite to the dipole moment. But in case of potential, here you see in case of potential, in case of that is V, in case of potential it is Q by 4 pi epsilon naught R. In case of potential, here you see in case of potential it is Q by 4 pi epsilon naught R. Here, if Q is greater than 0, then it will be positive, and if this minus Q by 4 pi epsilon naught R, if Q is less than 0. That means if the Q is negative, then the potential will be minus, and if the Q is positive, it will be plus. So this is the very important fact while calculating. If it is negative charge, it will be minus. If it is positive charge, it will be positive. So these are the important points which I want to tell you here that your electric between electric field and your potential. Here you find that in electric field, what did you find? In electric field, you find that the formula is Q by 4 pi epsilon naught R square. So here you see that E is proportional. Your electric field. In your electric field, it is proportional to R, 1 by R square. But here your potential V is proportional to 1 by R. So these are some of the important results which is useful for your competition, or as well as for solving problems, as well as for your board exams. So this is the most confusion which most of the students have, if whether you have to, this Q will be positive or negative in V, or Q will be positive or negative in E. So such type of points I am going to clarify today, which will help you for solving the problems, or solving the problems. So now here some of the things which must be clear with you. So here you see, when there is a charge Q, let us take positive charge, there is an electric field. So when there is a positive charge, that means there is an electric field. And when there is an electric field, so if you bring another charge, let this be take as a capital Q. If you bring another charge plus Q, you have to do work against the repulsive force. You have to do against the repulsive force. So there is a work done, and that work done is the potential energy of charge Q. See the definition. That is the potential energy of charge Q at some point. If you are bringing from B to A, so this is the potential energy of charge Q. See the definition. So if you want to find the potential, energy of charge Q, at point A, so you have to bring this charge Q from infinity to the work done. That is the work done in bringing the charge Q from infinity to this point A. Then it is the potential energy of the charge Q. See the definition, potential energy of the charge Q at A. This is the potential energy of the charge Q at A. This is the most important point. And for potential, if you go for potential, then you have to bring a unit positive charge. Then you have to bring a unit positive charge. You have to bring a unit positive charge from infinity. Unit positive charge from infinity to A. So that will be potential at A. So this will be potential at A. So see here, if you bring this, this is the important point, that is you see the definition. If you bring a charge Q plus Q from infinity to the point A, then it is called the potential energy of charge Q at A. But if you bring a unit positive charge from infinity to A, then it is the potential at A. Then this is the potential at A. So this is represented as V, and this is represented as U. This is the potential V. So remember that whenever we take plates, we say potential, not potential energy. Whenever we take plates, so whenever we take plates, two plates, we say potential difference. We say potential difference. Not potential energy difference. We say potential difference. We say potential difference. We do not say potential energy whenever we take plates. when we take plates, we say that there is a potential difference between the two plates. So here, these things you must be remembered. And potential energy of the, this is the charge Q. If you bring from B to A, that is the potential energy of charge Q from when at A, when you bring it from B to A. So this is the change in potential energy of the charge Q. This is the change in potential energy of the charge Q. But this is the but if you bring a unit positive charge from infinity to this A, remember, if you bring a positive, then it is the potential at A. So see the difference. Potential at A. Here this is U by Q, and here this is U. This is U by Q, and this is Q. So if you take plates, we say potential, and if we take two plates, we say potential difference, not potential energy difference. So these are the important facts which you must keep in your mind, and this will help you in calculation and to understand the theory in details. So in case of battery, we say that the potential difference between the two terminals, because they are the plates. We do not say the potential energy difference between the two terminals of the battery. We say the potential difference because there is a plate. We consider it as a plate. There are the two terminals as a plate, and we say that the potential difference, not potential energy difference. So I want to clarify you some of the important facts which are very important which will make your physics more clear. So up till now, I think you have understand what is electrical electric field. So in electric field, it is a vector quantity, no doubt, but the sign of the charge Q will be always positive while calculations. But in case of potential, if it is minus Q, then it will be minus, and if it is plus Q, then it will be plus. So the direction of the electric field, I have told you how electric field becomes negative. So in case of dipole, if the electric field is in the direction of the dipole moment, that means if it is in the direction of the dipole, then we take the electric field as positive. But if it is in the direction opposite to the dipole moment, we take the electric field as negative. But the sign of Q will be always a positive. So this thing I want to clarify you while doing the calculations. And these are the most basic important point. But in case of Coulomb's law, when you calculate the force between the two charges, here the sign of the charge is not concerned because we are taking the magnitude. So if these points are clear to you, you will be able to easily solve the questions, easily solve the mathematical questions. Now, my another point here is that today I'm going only to discuss the important points, the most important points which most of the students feel little bit difficult, and it remains in whether it must be plus, it must be positive. So it remains in a dilemma. So to clarify that all those points, today I am dealing with all such points. Now here again you see some important fact that your dielectric, it is a non-conducting material. It is a non-conducting material. So one of the most important point here is that it is a non-conducting material. It is a non-conducting material. It is a non-conducting material. Dielectric, it is a non-conducting material. Dielectric, it is a non-conducting material. So here what I want to tell you that between a conductor, the most important point is conductor. In the conductor, the free charges, when an external electric field is applied, in a conductor, due to this external electric field, induced charges are developed inside the conductor. Induced charges are developed inside the conductor. Induced charges are developed inside the conductor. and the direction of the electric field inside the conductor is opposite to that of the external electric field, and after some times the external electric field is equal to the internal electric field. So the net electric field inside a conductor is zero. Remember that this is the very important point. The net electric field inside a conductor is zero. Remember that the net electric field inside a conductor is zero. Inside the conductor there is no electric field. Only the free charges, they drift when an external electric field is applied. Only the free charges at the surface, it drifts when an external electric field is applied. The electric field inside a conductor is zero. Electric field inside a conductor is zero. This is a very important point. And now similarly, if a conductor, it has a cavity, even if there is a charge, outside the conductor, but the electric field inside the conductor is zero. Electric field inside the conductor is zero. Let us take a conductor with a cavity inside. Even if there is a charge outside the conductor, the electric field inside the cavity is zero. Such are the important conclusions here. Now in case of dielectric, here you see that in case of dielectric, when an external electric field is applied, the polar molecules, they try to align themselves. They try to plus minus, like this, plus minus. They align themselves in the direction of the electric field. They try to align the direction in the direction of the electric field. So there is a dipole moment. So that's net dipole moment will be the sum of all the dipole moment of each molecule. The net dipole moment will be the sum of all the dipole moments of each molecule. So what happens at last? You see here that here inside it is neutralized, the charge is neutralized, but here there is a charge density arises, that is negative charge density, and this on the other side there is a positive charge density. There is a development of positive charge density. So here you see that in a dielectric, the inside it is inside the charge are neutralized, but at this surface here negative charge, this remains. Here negative charge develop, and here the positive charge develop, because you see it is not neutralized. It is not only the internal part of the dielectric is neutralized. So you get a charge density, negative charge density at this plate and this side, and a positive charge density at this side. So what happens here? It acts like a charge plate. Here this two acts like a charge plate. So if you consider a volume of the charge, and if you consider volume of the charge, then there is a charge density, and it acts like a two charge plates. The dielectric acts like a two charge plates. So this is the here in dielectric there is no movement of free charge, but in conductor there is movement of free charge, but in that there is no movement of free charge. Only the polar molecules, they try to align themselves in the direction of the external electric field, and the electric field created here is in a direction opposite to that of external field. But here the net electric field inside the dielectric is not zero. So these are the important points which you must know and you must remember. So here you come to another point, that is in case of you come to the capacitance. So here you see that in capacitance, if you see when they derive the formula, when you see that in capacitance, this is the most important point, capacitance. which you will use in while solving problems. Here you see that when a dielectric is inserted in a capacitor, that is a parallel. First there is a parallel plate and see here there is vacuum of air, that is q charge minus q charge. This is the capacitor. When there is a vacuum or say air, then your capacitance, this C naught is equal to q by V naught, that is the difference between the two, potential difference between the two plates. Here you see that one of the important point, here you see that you will see in your chapter that when you derived, you are deriving the formula, that is what will happen to the capacitance of a capacitor if a dielectric is inserted in between the plates of a capacitor. What will happen? You have seen that there is a derivation in your book where you will see that between what will be the effect when a dielectric is inserted between the two parallel plates of a capacitor. What will happen? So here you see that first case, when there was no dielectric, your capacitance was q by V naught. And second, when the dielectric was inserted here, when a dielectric, then your capacitance becomes q by V. You see that the capacitance is q by V. While you have seen that when there is a vacuum or say air, then initially when there is no dielectric, then your capacitance of the capacitor is this. And when you inserted a dielectric, your capacitance is q by V. So here you see that the charge remains the same. Whether you insert a capacitor, dielectric or not, but your charge remains the same. So why I am giving the stress here, the charge remains, because this will help you in any type of calculation of problem or any type of conceptual questions to answer. This will help you. So here, no doubt, when you insert a dielectric, the capacitance of the capacitor increases. But here, capacitance of the capacitor increases, no doubt. But here you see that your charge remains the same. Your charge q remains the same. This is the case when dielectric was inserted. And this is when there was no dielectric. You find that your q remains the same. So these are some of the important factors which will help you in conceptual questions or in doing conceptual questions as well as in solving the problems. There may be question that what will be the capacitance of a capacitor if a dielectric related with the when there was no dielectric, and when a dielectric is inserted, then it may ask that what is the relation between these two. So this will help you to solve such type of problem. So this is all about your important fact about capacitance. But in capacitance you see that that is Q is equal to CV. Q is equal to CV. That means Q is equal to CV here. That Q, that means the V. Work done in bringing a unit positive charge from this plate to this plate. This is the work done. This V, it is the work done in bringing a unit charge from this plate 1 to plate say 2. This is the work done. This is the V. So remember this plate here, this is plate, so we are considering its potential. Here we do not consider potential energy difference, we consider potential between these two plates. And this V, it is the work done. In the formula Q is equal to CV, remember this V, what is V? It is the work done in bringing a unit positive charge from this plate 1 to plate 2. That is the work done, that is the potential. So These are the important points with definition you must remember. So for any competition, or these are the basic lines which you must remember. Now another important point here, it has been told in your in your book, that is the you have in for Coulomb's law, that is Q1 and Q2, that is the force between the force Q1 and the Q2. So here you see that. Now here an important fact which is given in your book, important fact you must know, that in Coulomb's law Q1 and Q2, these are for electrostatic. Now suppose if Q1 and Q2 they are accelerated, they are in accelerated motion, they are in accelerated motion. The Coulomb's law which you have which it has been stated, it is for electrostatic. Now suppose if Q1 and Q2 is accelerated. Now Q1 and Q2 is in accelerated motion. Q1 and Q2 is in accelerated motion. So here cause and effect, that is cause and effect, that is cause, that is the force which Q1 exerts on effect, that is Q2. Cause, that is the force which Q1 and the effect, that is on Q2. So here in electrostatic it is the charge were stationary. Now an important fact has been given here, that if Q1 and Q2 is in accelerated motion, cause and effect, cause, that is the force Q1, and effect on Q2, it does not occur simultaneously. Remember, it does not occur not simultaneously, instantaneously. It does not occur instantaneously. It does not occur instantaneously. Remember that it does not occur instantaneously. That is see, when Q1 and Q2 is in accelerated motion, cause and effect, cause, that is, I am clarifying you, cause and effect, cause, that is motion, cause, that is motion of Q1, and effect, that is force on Q2. Cause and effect. When Q1 and Q2 is in accelerated motion, then the cause and effect, that is motion of Q1, and the effect, force on Q2, the motion on Q1 and force on Q2, they do not occur instantaneously. You remember that they do not occur instantaneously. They do not occur instantaneously. There is a time delay. You remember that there is a time delay. If Q1 and Q2 is in accelerated motion, the cause and effect, that is motion of Q1, and the effect, force on Q2, this does not happen instantaneously. There is a time delay. There is a time delay. Now here there is a time delay. So the cause and effect, it does not occur instantaneously. Motion of Q1 and effect, that is force on Q2, there is a time delay. So what happens? So here what happens? The accelerated motion of charge Q1, the accelerated motion of charge Q1, the accelerated motion of charge Q1 produces electromagnetic waves which then propagates with the speed of the light c and reaches Q2 and cause a force on Q2. Here again I am telling you that the accelerated motion of the charge Q1 which propagates with the speed of light and exerts a force, reaches Q1 and exerts a force on Q2. So here again I am going to tell an important fact which has been told, it has been stated here. That is here in this is the Coulomb's law. It was on electrostatic. But now what happens if Q1 and Q2 is in accelerated motion? Cause and effect, that is motion of Q1 and force on Q2, that is cause and this is the effect. This does not happen instantaneously. There is a time delay. So because of this time delay, the accelerated motion of charge Q1, it propagates. Accelerated motion of charge Q1, it propagates with the speed of the light. It propagates with the speed of the light. Remember, it propagates with the speed of the light. The accelerated motion of charge Q1, it propagates with the speed of the light. It propagates with the speed of the light, reaches Q2. It reaches Q2 and exerts a force on Q2. What I want to tell you that the accelerated motion of charge Q1, it propagates with, means accelerated motion of charge Q1, it produces electromagnetic wave. It produces electromagnetic wave. This I want to stress here. That is the accelerated motion of charge Q1, it produces electromagnetic wave which propagates with the speed of light, and reaches Q2 and exerts a force on Q2. So this electromagnetic waves, the creation of the electromagnetic waves. So this is an important fact which has been told in your book, that if Q1 and Q2 is in, I am repeating the same, if Q1 and Q2 is in accelerated motion, the cause and the effect, that is cause the motion of Q1 and the effect the force on Q2, it does not occur instantaneously, there is a time delay. And this time delay, that is the accelerated motion of charge Q1, it produces electromagnetic waves. It produces electromagnetic waves which propagates with the speed of the light and reaches Q2 and exerts a force on Q1. And another important fact it is given here, that when in a conductor, when an external electric field is applied, in a conductor, the free charges drift. The free charges drift, but the free charges drifts, and when there is no electric field, the charges redistribute themselves. That means they redistribute themselves. That means they comes to the original position. This is a very, very important fact, which is a most fundamental fact, which most of the students are not aware with it. So why I am giving the stress in such type of points here, electromagnetic waves, the creation of electromagnetic waves. And here you find that whenever you on the switch, the current flows, and when you off, what happens? All the charges it redistributes. That means they come to their original position. So whenever in a conductor, when an external electric field is applied, the free charges they drift. But when there is no electric field, they redistribute, that means they comes to their original position. All the charges, they comes to their original position. So these are some of the important facts which this is the practical application, because you have find that whenever in your house, when switch is on, then the current flows. When the switch is off, all the charges that it redistributes, that the flow of the electrons, they redistributes it, and redistribute. So the conductor, inside the conductor, all the electrons, they get redistributed and they come to their original position. So these are some of the important point about charge, electric field, potential, work done, and work done. These are the so that the topic has been designed like this. Q charge. This Q charge has created an electric field. So when there is an electric field, so there is potential energy. When there is potential energy, that means there is a potential. So now I am going to shift from here to the Ampere circuitry law, because here in this the Gauss law is very important. Gauss law is very important because Gauss law, it helps you to find. And another important point here is in electrostatic, the electric field on the surface, electric field on the surface is perpendicular to the surface. That means electric field is always perpendicular to the surface. In electrostatic, you remember that. You must remember that in electrostatics, that is the field on the surface is normal, means it is perpendicular to the surface. The electric field must be normal to the surface. It must be normal to the surface. So here in this, the most important point here, these are the important point. Another important point here is that Coulomb's law, and this Coulomb's law, in Coulomb's law, Coulomb's law, the charges are always taken as a positive, because we are considering, while we are considering only the magnitude. Similarly, you have seen about the electric field, you have seen about the potential. Now, and here Gauss law is very important, because the Gauss law helps you to find out the electric field at any point, outside the surface of a body, a charge flowing through a body. To find means the Gauss law is very important, because it helps you the charge, because of this charge, uniformly distributed charge inside a conductor, what will be the electric field at this point. You can find it out at this point. You can find it out with the help of the Gauss law. Now here I am going to this Ampere circuitry law. I am going to Ampere circuitry law. Now, before going to the Ampere circuitry law, I am going. I want to tell you one more important point, that is, when a dipole is kept in an electric field, when a dipole is kept in an uniform electric field, say this is the dipole, it is kept in an uniform electric field. So here the force is QE. This is the field E. When it is kept in an external electric field, and here the force is minus QE. This is the force here, and this is the force. So while calculating the potential energy, remember that this is a very important point. While calculating the potential energy, the initial position is taken as pi by 2. Initial position is taken as pi by 2. Why? Because the work done, here the force is in this direction. So work done to rotate it work done to rotate it, to work done to root pi by 2, work done to rotate it in a work done to rotate it when theta is 90 degree, that is the work done to rotate it becomes these two work dones, these two work dones becomes 0. These two work dones is when to rotate it to 90 degree, to rotate it to 90 degree. That means work done, we are doing work, that is potential energy, we are doing work against the existing force. This is the force, we are doing work done, we are doing work against the existing force. So the work done in bringing this to 90 degree, work done in bringing this to 90 degree is 0. Is 0. Your work done is 0. So work done is 0. So in bringing in work done, that means potential energy. Work done, that is potential energy. That means you are doing work against this existing force, against this existing force. When you rotate it to 90 degree, the work done is 0. So initially the theta naught is considered as pi by 2, while deriving the potential energy of a dipole when it is placed in an electric field. Now, and before going to Ampere's circuit law, Ampere's circuital law, before going to Ampere's circuital law, I want to tell you one more important thing about capacitor. That is, in the outer region, your electric field is 0. In the outer region, your electric field is 0. Inside the capacitor, your electric field is sigma by epsilon naught, where sigma is the surface charge density. This is the surface charge. This is the surface charge density. This is the surface charge density. Another important point, this is a very important point, that is in a capacitor, the electric field in the outer region is 0. In the outer region is 0. In the outer region it is 0. Electric field in the outer region it is 0. In the outer it is 0, and the electric field inside the capacitor is sigma by epsilon naught. This is the important fact which was left. So all these things you must remember. Now I am moving to Ampere's circuit law. Suppose Ampere, this is a long wire, long wire. That means it is moving out of the plane of the paper. This is out of the board, long wire, and current I is flowing through this wire. This is a long straight wire. This is a long straight wire. This is a long straight wire, and the wire, it is moving out of the plane. That is moving out of the plane of this board of this paper. Now here you have to find suppose what is the magnetic field at this point. So we consider magnetic field as, we consider this as an Amperian loop. This we consider like Gaussian surface. Here we consider an Amperian loop. The most, why I have selected this, the most important point here is that this is the Amperian loop. This is the long straight wire. This is the long straight wire. This long straight wire where current I is flowing through it. Current I is flowing through it. Long straight wire where current I is flowing through it. And this is the Ampere loop. Suppose here you want to find the magnetic field. So remember that your magnetic field is always tangential. Remember that your magnetic field is always tangential. At this point, and your DL is also tangential at this point. That means your angle between B and DL is 0. Your angle between is 0. Remember, this is the very important point. Your magnetic field is tangential. This is the Ampere loop. This is the long wire, straight wire carrying current I, and your this magnetic field is at any point is tangential, and this dl is also tangential. So according to Ampere circuit law, cyclic integral of B dl, that is the cyclic integral of B dl, this will be this is nu naught nu naught I, this is nu naught I, but here the angle is, so your angle is cos theta, dot product, your cos theta is 0, so 1, so here your B and cyclic integral of dl, this will be nu naught I. So this is, if this radius is r, so B into 2 pi r, that is equal to nu naught I. So B is equal to nu naught I by 2 pi r. This is the magnetic field. All these things you know, but the important point here is that in the Ampere loop, your magnetic field at any point is tangential, and dl is also tangential, and the angle between B and dl is 0. This is the most important point here. This is the most important point, and this is the magnetic field at this point because of this long straight wire, carrying current I. Now the important point in solenoid. Remember that in a solenoid, the magnetic field outside is it approaches 0. That means you can say the magnetic field outside is 0. The magnetic field is only along the length of the solenoid. So according to Ampere circuit law, BL is equal to nu naught IE. It is the current. In the solenoid. It is the current in the solenoid. So magnetic field inside a solenoid is nu naught N I. So magnetic field inside a solenoid is nu naught N I. So the important point here is that magnetic field. Remember that the magnetic field outside the solenoid approaches 0. Like in capacitance, the electric field on the outer region is 0. Only the electric field is inside the capacitor. Similarly, in solenoid, the magnetic field outside approaches 0. The magnetic field is only inside the solenoid. These are the important points you have to remember. So the magnetic field inside the solenoid is nu naught. It is nu naught N I. Let me write nu naught. And number of turns, and I is the current in the solenoid. Now let us consider this is a conductor. And the current I is flowing through it. Now we have to find magnetic field, say R, and another magnetic field, this R, inside the conductor, and this is the radius of this conductor A. So here there are two cases. We have to find the magnetic field when R is greater than A, and the second case when R is less than A. There are two cases where A is the radius of this conductor and current I is flowing through this conductor. So here again an Ampere loop. This is the Ampere loop. That means here this is your conductor. So Ampere loop will be this. Your Ampere loop will be this, which I have drawn by the dotted line. Your Ampere loop will be this. This will be the Ampere loop. This is the Ampere loop. Let me make it a circle. This circle is like this. This circle is the Ampere loop. So here the magnetic field you have to find at a distance r. So from your Ampere circuit law, your B into 2 pi r, that will be equal to nu naught I. So B will be nu naught I by 2 pi r. That is when R is given, when R is greater than A, when R is greater than A. So if your R is less than A, if your R is less than A, if your R is less than A, then the current through this section, current through this section, that will be equal to pi R square by pi A square into I. This will be the current in this section, inside this ampere loop. This is the ampere loop, current inside this ampere loop. See here, this ampere loop, this ampere loop. Inside this ampere loop, current will be this. So your magnetic field will be B 2 pi R, B 2 pi R, that will be equal to, that is your B into 2 pi R, that will be equal to your nu naught and pi R square by pi A square into I. This will be your magnetic according to Ampere's circuit law, when R is your less than A, because the current inside this ampere loop will be this. This is the current inside the ampere loop. So here your B, you will see that B, this pi cancels out. So here this will be nu naught I, nu naught R by 2 pi A square into I. This will be your magnetic field when R is less than A. What do you find here? You get an important conclusion, that is magnetic field outside. The magnetic field outside this conductor, magnetic field outside, here you see the magnetic field outside this conductor is proportional to 1 by R, and the magnetic field inside the conductor is proportional to R. This is the important result which you get from here, that the magnetic field outside the conductor is 1 by R and the magnetic field inside the conductor is proportional to R. This is an important conclusion. And the last important conclusion which I am going to tell you, that is the last important conclusion that I am going to tell you. These all things you must remember. And the last, that is, what is magnetic movement? What is magnetic movement? What is magnetic movement? What is magnetic movement? This is the last important topic which I am going to deal. A current carrying loop, that is any loop, a current carrying loop is called the magnetic movement of the current loop. It is called the magnetic movement movement of the current loop. This is called the magnetic movement of the current. What is magnetic movement? Any loop, current flowing through any loop is the magnetic movement of the current loop, where magnetic movement is equal to I into area vector, I into area vector. This is the any loop carrying current is this is the magnetic movement. So these are the important factors you must remember, which will help you for both in any competition, either for NEET or for board. And these are the basic concepts which will help you to solve the problems. So and another important point here, which I have left here in electric current, another important point which I have left in electric current, that is potential difference. That is the potential difference between the two ends of a battery when it is connected to a circuit is epsilon minus IR. That is epsilon, it is the electromotive force, and R is the internal resistance of the battery. Internal resistance of the battery. That is this is the potential difference between the battery. Potential difference between the battery is equal to epsilon minus IR, where when this battery is connected to a circuit, this will be V when it is connected to a circuit. But when it is not connected to a circuit, then the potential difference between the two plates of the battery will be epsilon. That is electromotive force. This is an important point to remember. This is an important point to remember. And the next important point, the free charges which an electron moves, the free charges which the free charges which moves on the surface of a conductor, the free charges which moves on the surface of a conductor when an external electric field is applied, these charges moves with the velocity, and that velocity is called drift velocity. That velocity is called drift velocity. Drift velocity. Remember that the drift velocity. This is very important. They move with the drift velocity, which is represented as VD. This is all about for today. I have dealt with some of the important problems, because your NEET exam is near, and keeping in view, I have made a revive on this because this time on this topic the weightage is more weightage is given. So keeping in view all the weightage of this year's in NEET exam, I have dealt with only the important points which most of the students remains in dilemma. So I have dealt with only the important points here. So this is all about today.